So this lecture is going to be about electrolytes, non-electrolytes, strong electrolytes, weak electrolytes, and identifying them. So when we talk about electrolytes, we talk about some kind of compound of some kind that is in a aqueous solution, meaning it's just been added to water. For example, sodium chloride, your generic table salt, could be added to water to make what we call a solution. And with these solutions, there's a couple of things we can say about them. We can say they are either homogeneous or heterogeneous. And homogeneous mixture is when you have two or more substances and you can't really tell there's two substances there. So for example, if I put a glass of, just regular plain water in front of you, salt water or sugar water, you wouldn't be able to tell the difference by visually looking unless you tasted them. That's the only way you'd really be able to find the difference there. So when we have these solutions, they can either be in a gas form, a solid form, or a liquid form. And we generally have a solvent and a solute. The solvent is the thing that dissolves the solute. The solute is the thing that is being dissolved. The solute is generally the one in the smaller amount. Excuse me. So if I had, again, salt water, my salt would be the solute and the water would be the solvent. When we have these solutions, they can be electrolytic solutions or non-electrolytic solutions. And all we mean by that is if we're talking about having an electrolytic solution, that means there's an electrolyte in some way, shape, or form in the solution. It is something that will dissolve in water and it will conduct electricity. A good example of this comparatively is sodium chloride and sugar, just comparing them. So sodium chloride, as you can see here, it will break up into its individual ions. When these ions are formed in solution, that allows electrons to flow if I have the proper setup, which will be able to conduct electricity. On the flip side to that, sugar molecules do not break up into their individual ions or their individual elements as ions. They simply break apart into individual whole molecules. So what does this really look like? If you remember, water has a dipole moment. It is polar. It has partial negative and partial positive ends. Well, when the sodium chloride is put into water, the partially negative ends of water become attracted to the positively charged sodium, like we see here, and they surround it. The chloride ions that are negative are attracted by the partially positive hydrogen ends of water, and they form what we call a solvent cage. They form a solvent cage around these two ions because water is polar and their positively and negatively charged ends are attracted to the opposite positive or negative charged sodium or chloride ion, depending on which one we're talking about. Sugar, on the other hand, does not break down into the individual carbons, hydrogens, and oxygens. So water just separates them each as a whole entity and completely surrounds them, allowing the sugar molecules to disperse throughout the whole thing. This is why when we put sugar in a sweet tea or coffee or hot tea, etc., you can taste the sweetness throughout the entire drink, not just in one spot, perhaps maybe at the bottom or something. Same with salt water, but it just does it differently. If you have salt in water, because of these solvent cages that form, you can taste the saltiness in the water throughout the entire cup. When we talk about this breaking down and breaking apart into ions, we refer to it by way of dissociation or ionization. So dissociation happens with an ionic compound, and that ionic compound breaks apart into its constituent ions. So the example we just saw was sodium chloride. The sodium ion would go out into solution and the chloride ion would go out into solution. They were no longer a together substance. They separated out. Ionization is when a molecular compound forms ions. So dissociation has to do with ionic compounds, and ionization has to do with molecular compounds. With this, we can talk about acids and bases, And we're going to refer to acids for now. We're going to define acids as those things which give off a hydrogen in solution. And bases are those things which give off a hydroxide ion in solution. And the amount at which they ionize or dissociate has to do with the amount or their strength, basically. So a strong electrolyte is either an ionic, acid, or base, one of those three things, that disassociates, we can assume 100%. And those are the strong electrolytes, or what we can call strong acids or bases. They will 100% dissociate. So the rule is any water-soluble ionic compound will dissociate completely upon dissolving. Here are your lists of strong electrolytes. You'll notice in this case we're talking about acids. Here's your list. You need to know these. And what this means is they will 100% dissociate into their individual respective ions. So hydrochloric acid will, in water, produce hydrogen ions and chloride ions. For example, nitric acid will dissolve 100% to form, again, your hydrogen ions and your nitrate ions, etc., etc. You need to know these. If you know these, you can assume every other acid is a weak acid. Now, I want to be very, very clear about something. We don't call them strong acids and weak acids because of the strength of their bonds. Strong acids actually have very weak bonds between the hydrogen and the anion. And because those bonds are very weak, they very readily and easily dissociate or ionize into their individual ions. For example, hydrofluoric acid, HF, is considered a weak acid. It is weak because the bond between hydrogen and fluorine is very strong. Because it is very strong, it takes a lot for it to break apart, a lot of energy. Also, I just want to mention here that for sulfuric acid, because it's a polyprotic acid, meaning there's more than one hydrogen, proton, hydrogen, poly, many, it's a polyprotic acid. For the purposes here, and as far as solving for everything and understanding, we're only going to worry about the first deprotonization or the first removal of a hydrogen. You will find that this would be step 1, this would be step 2, because the hydrogens come off one at a time, not all at the same time. Weak electrolytes are electrolytes or acids or bases, so ionic compounds, acids or bases, that ionize or dissociate relatively less than about 5% of what's present. You'll notice in these examples here hold on, I'm trying to get my highlighter up, of these balanced chemical reactions, there's a single arrow in one direction. You'll notice for weak, there's a double arrow. And what that means is, because they're very weak and roughly only about 5% of what is present ionizes, this is what we call a reversible reaction. Both the forward and the reverse are happening simultaneously. So I want to just note that ammonia does not actually ionize by breaking apart into ions. So when ammonia, which is NH3, it does not break down into this. That does not happen. What actually happens is ammonium ion picks up a hydrogen ion from solution. Where's that hydrogen ion coming from, you might ask? Well, you have to remember that if we're talking about an aqueous solution, water is present. Water is the solvent. So water at any given time also exists in a reversible reaction. So at any given time, we have 3 species of the water present. Okay, so at any given moment, any of these 3 are present. I want to also notate for you that H3O plus is the same thing as saying H plus. Okay, it means the same thing for the purposes of what we're doing. So these hydrogen ions are floating around in solution if it is aqueous because that was the solvent. So there is a hydrogen ion or a proton in solution somewhere, and this ammonia molecule will pick it up and then become charged. Okay, because it's gained an extra hydrogen, therefore losing one more electron. So when we're identifying strong and weak electrolytes, you need to be able to understand, first of all, is it ionic or molecular? That's your first question. If it's ionic, meaning cation and anion, it will dissociate into its individual ions. If it's a binary compound that has a metal and a nonmetal, it's always going to be ionic. They say almost always, but you know, in chemistry, we often cannot exclusively say 100% or 0%. Any ionic compound that is soluble in water is a strong electrolyte. So we have strong acids, strong bases, and strong electrolytes. The strong acids are previous couple of slides with your list. I can't recall if there's a list of strong bases in this PowerPoint. If not, I will provide one for you. There's about 7 of them. And then if it's a soluble ionic compound, metal, nonmetal, then it will be a strong electrolyte. How do you know if it will dissolve in water? Well, you need to go to your solubility rules for that. If there's no metal cation or the ammonium cation, it is considered molecular, meaning all nonmetals. In this case, you have to determine if it's an acid or not. We can decide if it's an acid just based on the formula. So for example, HCl versus C6H6, these are both compounds that only contain nonmetals. So we can look at HCl and say that is an acid simply because that hydrogen is out front. If there's no hydrogen out front, then it is not an acid. So for example here, if you're looking at an electrolyte, whether it's a non-electrolyte, weak electrolyte, or strong electrolyte, you need to determine what you have, okay? So it looks like I'm having a little bit of issues with some pictures here, so let me just skip ahead and see if it's not. Okay, in the original PowerPoint, there is a flow chart that is associated with these, and the flow chart basically says, okay, is it ionic or molecular? Okay, the first one, A, methanol, it is molecular. There is no metal present or ammonium ion. So then the question is it an acid or not an acid? And the answer for methanol is it is not an acid because there's no hydrogen out front. Because it is not an acid, we can say this is a non-electrolyte. It will not ionize into its individual ions, and therefore it will not conduct electricity, so it is a non-electrolyte. Sodium hydroxide, is it molecular or ionic? Well, there's a metal and nonmetals, so it is ionic, and sodium hydroxide is actually a very strong base. Strong acids and strong bases are strong electrolytes. So this is going to be considered, because it's an ion and it is soluble in water, I know that based on my solubility rules, this is going to be considered a strong electrolyte. Ethylamine, it has all nonmetals, not the ammonium ion, or not ammonia, but a very, very close family member of ammonia. Okay, you'll remember ammonia is NH3. This NH2 here is an amine. So this is going to be considered a weak electrolyte. Okay, and then hydrofluoric acid, we already talked about this. It is a weak acid, therefore it is a weak electrolyte. We know it's an acid because of the hydrogen and fluorine. Shh, quiet. Sorry, guys. I don't know where all my flowcharts went. Please go look in the original PowerPoints for this. Okay, so we're going to start. We've already done solubility guidelines and rules and ionic compounds, etc. So that was in the previous lecture for this chapter. So now we're going to talk about molecular, ionic, and net ionic equations. So molecular equations are the equations where everything is just written out as the compound formulas. They are all neutral. It is balanced. There you can clearly see there are no charges here. Everything is neutral. And it's all together in their original formulas. So PbNO32, this right here, it's neutral, nothing is charged. Same with sodium iodide, neutral, nothing charged. These are your molecular equations. If I compare that to ionic equations, what we see here are charges within everything, and everything that is soluble or could be soluble in water is written out in its individual ions, paying attention to both coefficients and charges and subscripts, ensuring that we have a balanced ionic equation. Now, your net ionic equation has to do with what's really doing the work here, what is really involved in this reaction. And we find net ionic equations by getting rid of what we call spectator ions. They're the ones that are present in solution, but they don't really contribute at all to the reaction itself. They will stay aqueous, no solids are formed, they simply just stay as is. So because they're the same on both the left and the right side of the reaction arrow, we can cancel them out, and what's left is our net ionic. So in this case, here we have the drawn out individual ions from some reaction. In fact, let me write the original equation so we can have some full vision here. So it's sodium sulfate, so this would be Na2SO4 plus, let's see, barium hydroxide. These are aqueous. Yields sodium hydroxide and barium sulfate. Okay, so that's our original equation. Now, if we go to our solubility rules, we can see that sodium sulfate is soluble, barium hydroxide is soluble, sodium hydroxide is soluble, and barium sulfate is an insoluble solid. Okay, so that means in their in their ionic equations, sodium, let me balance this right quick. Let me make sure I'm balanced here. 2, 1, 1, 2. Okay, I'm good. I'm balanced. All right, so if we look at sodium sulfate, it is going to break apart into its individual ions because it is soluble. So that means we have to put a 2 in front of the sodium ion because there are 2 of them. And the sulfate is a 2 minus overall anion. I know that because I'm really starting at this point to almost memorize the polyatomic anions, and it's got a 2 minus charge on it associated with it. And there's only one of them. So then barium hydroxide, because it also is soluble, is going to break apart into its individual ions. And I have a typo. Sorry, guys. Now, we have to say, okay, barium is a 2 plus charge. There is no coefficient in front of barium hydroxide. So we just write Ba2 plus because, again, barium is a 2 plus charged cation. And the hydroxide is an OH minus. That's its charge. And I have to put 2 because there are 2 of them present. All right. Then sodium hydroxide on the product side is also soluble. So it's going to break into its individual ions. Although there are no subscripts here, the 2 in front to balance this equation, the 2 NaOH, has to be taken into account because what that means is there is 2 sodiums and 2 hydroxides. And then finally, barium hydroxide just stays as is. It is a solid, so it does not break apart. Okay, it stays in its own true entity. So solids, diatoms, remember those are H2, N2, O2, etc. Carbon dioxide and liquid water stay together. They do not break apart into their individual ions. Okay, you gotta remember these. You gotta know these. Now that I have my ionic equation written, I can go ahead and look and say, okay, what's going on here? Well, what's going on is that I have sodium on the left and sodium ion on the right. They will cancel out. They are the same on both the left and the right side of the arrow, so they will cancel out. I look at sulfate anion. There's no sulfate anion on the right-hand side, so it stays. I look at barium ion. There's no individual barium ion on the right-hand side, so it stays. Hydroxide, there's one hydroxide. Here's another hydroxide, both on the left and the right-hand side of the equation. So those go away. They cancel out because they're spectator ions. So what's left that did not cancel is my net ionic equation. And that's where we get our net ionic equation from. So let's just look at a few more examples here. If I have this main molecular equation here, that's my main molecular equation, I can look at my solubility rules and I can say, okay, what's going on here? Well, potassium chloride is soluble. Lead 2 nitrate is soluble. All nitrates are soluble. Potassium nitrate is soluble. Again, all nitrates are soluble. And lead 2 chloride is an insoluble solid. I know this because, again, if I look at my solubility rules, I will see that although chloride ions in the halogens are generally soluble, lead is an exception to that rule. It was lead, silver, and mercury. So because lead is an exception, that makes lead 2 chloride insoluble solid. So once I know that, what I can do is I can say, okay, potassium is going to break up into its individual ions, and I need a 2 out in front because it's balanced with a 2. Even though there's no subscripts, it's balanced with a 2. So I need to include to say there are 2 potassium ions and 2 chloride ions. I want to mention something else just quickly. If, let's just say, pretend it was this. It's totally not. This doesn't exist. I'm making this up. But if it were this, then I would say 4 K pluses and 2 Cl minuses, because that 2 still applies to both. Okay, this 2 only applies to the potassium, and what this is telling me is that it would be something like this. So if I had 2 of these, I would have a total of 4 potassiums. I just wanted to make that very clear. Okay, so now I've broken down my potassium chlorides into their ions. Lead nitrate, lead 2 nitrate will do the same. Now, this 2 only applies to the nitrates, and so we need to put a 2 in front of the NO3 minuses. The PB does not have any coefficient or subscript. There's no coefficient for the nitrate either, so PB is just by itself a singleton, but its charge is 2. And I know that because I can do the reverse switcheroo, if you remember. And then my potassium nitrate on the right-hand side of the reaction arrow says, okay, I got 2 potassiums, 2 nitrates. I know that because there's a coefficient that applies to both the potassium and the nitrate. And then my lead is an insoluble solid, so it just stays as is. It doesn't break down. Now that I've done that, I can say, okay, I'm going to find the things that are the same on both sides. In this case, there's going to be potassium. Those are spectator ions. Chloride ions. Got one here. Nope, nothing on the right-hand side. Lead, Nope, nothing on the right-hand side. Nitrates on the right-hand side, right and the left-hand side. So all that's left are these, and that becomes my net ionic. I want to make something else very clear. If, for example, I had, hold on. If, for example, I had MgS solid on one side, and on the other side, I had Mg2 plus, these are not the same. They would not cancel out because one is a solid and neutral. The other one is a charged ion. They are not the same. You cannot cancel something like that out left and right. So here's another example. And you're going to have problems like this where I'm going to tell you sodium chloride reacts with lead 2 nitrate, write, complete, and balance a net ionic equation. All right. So what this means is you're going to have to be able to take the words and write the formulas from that, and then complete the chemical reactions. So sodium chloride is ionic, and based on my solubility rules, it is soluble, so I write aqueous. And then lead 2 nitrate. This 2, remember, refers to the charge on the lead, not how many of them there are. It is also soluble. All nitrates are soluble. Now, this would be considered a double displacement. If it's a double displacement, that means a solid will be formed. So I assume it's going to do the switcheroo, and then I'll check my solubility rules to make sure a reaction actually occurs. So switcheroo means the lead goes with the chloride, and the sodium goes with the nitrate. All nitrates are soluble. And then PbCl2, that is my solid. I know that because I've checked my solubility rules. Chlorides are generally soluble, but lead is an exception. All right, so now let me just make sure I'm balanced, and I'm not, so I need to put a 2 there and a 2 here. All right, so I know that this is soluble, 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 insoluble. So this means everything's going to break down into its individual ions. Okay, that's my ionic equation. And now my net ionic equation means I have to get rid of the spectator ions. The spectator ions are the ones that are the same on the exact same sides, left and right. So that means my sodium ions go away, my nitrate ions go away, and what I'm left with are these. So 2Cl minus plus Pb2 plus yields PbCl2. And that's it. It's that simple. I want you to go ahead and try this on your own and see what you can come up with for an answer. I'm going to just pause this, and then I'll write the answer down as the final, the ionic and the net ionic equation. So go ahead and pause and see if you can do this one on your own. Okay, That's your final net ionic equation right here. If you do not get it, or if you did not get the correct answer, you need to understand why and what you did wrong. If you are unsure, feel free to shoot me an email. That's it for this lecture. Next lecture is going to be on the Bronsted acids and bases and acid-base neutralization, which we're going to cover a little bit, but I really have already gone over the acid-base neutralization reactions in a previous lecture. Again, if you have any questions, feel free to let me know. Thanks, guys.